Okay, great. Let's see if this makes any energy sense. Okay, scroll the whole thing. It's like it listens to me. Okay. Did anybody still need our graph or our spring constant? It was up there a while. Okay. I'll take this down too when we'll solve some math problems. Okay. All right. So the spring force is pushing up. Okay. Let's consider our. Oh dear. And I need to scroll because we have a problem. Okay. The work done by the spring is the force, we'll put like a star, times the displacement. Okay, it's delta y for our case. It could be x, it could be d, whatever you want to label as displacement. I actually need to see my graph. It's very important. Okay, we don't need to see the very top, but you see that part? But there's a problem. The force is changing as it goes. Right, as I lower, like if I do this motion where so I start the spring unstretched, I have my 1.5 newtons on it, and I let it lower down. The spring doesn't cancel out all the force until I'm all the way down. In fact, I could start the spring, this is a different chapter, I could start the spring up high and it bounces. You heard the weights hit the table. It bounces up and down repeatedly. It's harmonic motion, we'll get that later. Okay, but so obviously this force isn't all the way engaged until I'm actually at that displacement. So what did we do last time, way back? We had a changing velocity. Is that what you're trying to say? Exactly. We might have started at rest, and we constantly accelerated in one direction, and then we had a final velocity, and we could still figure out how much it displaced. Right? Velocity times time, even when our velocity wasn't constant. How did we do it? Yeah, the area under the curve. Or we took the average velocity. For non-calculus pros, okay, since it's changing, springs are nice because they change their force at a constant rate. Okay, I was really freaking out for a minute there because some springs will not be F equals kx, they'll be F equals kx squared or kx cubed. You can manufacture a spring that's like super powerful over short distances, like engages right away. So yeah, what we have to do, it is symbolized, Isaac Newton realized, by the area under the curve, but it's also just used the F average. Your average force is 0 plus your final force divided by 2. Okay, because it changes at a constant rate. So if we multiply your average force by displacement, you get 1/2 of the final force at that displacement times, we would say, y squared. Or it can be x squared if you're on the x-axis, etc. And 1/2 fx squared for the work done by the spring. Oh, wait. I have to remember that I really have a dot product. And in a spring's case, they are always in opposite directions. The spring doesn't exert any force unless I pull it in the other direction. Okay, it would just snap back to normal. Okay, so the work done by the spring is negative. If the spring's doing negative work, oh look, that means gravity, and how much work is it doing? Okay, so I have to do 0.5 times my maximum force, which is 1.5, times 0.16. Oh no, I can do 0.4 meters squared. 4 squared. Okay. That's not bad. A teeny tiny amount of joules. I get 0.12 joules. And if I did 1/2, oh, it is F times Y. Excuse me, because this is 1/2 ky squared. Don't let me mess up. I did. I'm bad. 0.5 times 1.5 times 0.4 centimeters, which is 0.3 joules. Okay, that's better. Okay. Or if you try it, 1/2 kx squared. 0.5 times 3.125 times 1/4 squared is also, wait a minute. Oh man, that must be, yeah, I think it is. And it must be, that graph is super fishy. I must have not uh, done it right. Either I need to add a point 0.8 to all of those, or I don't know what the deal is. Well, it rounds to 0.3. Let's not mess with numbers then. And it needs to be negative. Okay, where did we get this energy? What's keeping the spring stretched? Gravity. Okay, exactly. So the potential energy of gravity decreased as I moved. But the increase in the potential energy, so the potential energy of the spring increased by mg. Well, it's like delta y, excuse me. That's okay. And so we could also say, if we wanted to do some fancy physics and solve a problem, mg delta y equals 1/2 ky squared. And it could technically be delta y squared. Okay, I had some trouble measuring my delta y's, so my numbers don't come out exactly. Sorry. Okay, does that make sense? As the weights get lowered, gravity's doing positive work. Okay, because gravity points down and they move down. Okay, but they don't speed up because that energy, instead of becoming kinetic energy, is going into the spring. So the spring potential energy increases even though the spring is doing negative work. Yes, that's right. The spring does negative work. The spring does negative work, and its change in potential energy is positive. Okay. You could think it's doing negative work on the weights by slowing them down. Okay. They actually do move. They gain some speed and then they lose it because I lower it. I interfere. Okay. So the spring is actually immediately taking away their kinetic energy and storing it inside itself. Okay, as spring potential energy. Does that make sense? You think you can keep the positive, negative work and positive and negative energy straight? I think with some practice, we probably can. Questions? Good. Okay. For once, I didn't mess it up. Okay, let's do a couple easy examples when you're done writing. Good. Okay. I can always flip back. Yep. This took a lot of time. I know. I encourage you to get your homework. Okay. I'm not sure if this is true. Another teacher told me this silly story. There really was a criminal nicknamed Jumping Jack Flash in London who would wear springs on his shoes or in his shoes, and he could jump over walls and fences and things to get away from the police. Uh, if we want to raise a 50-kilo person 1 meter above, just 1 meter. So let's start with y equals 0 and the spring compressed. Okay, and the spring is gonna. So at y equals 0, we do have some spring potential energy. Oh, we're going to have to... There's the bell. If we want to add 1 meter to his jump, okay, what energy must be stored in the spring? Actually, this is not... to store the spring, we need high kinetic energy. 55. How is it 55? Okay, but anyway, we want to lift the man 1 meter. So yes, in the meantime, it's going to go into kinetic, boost him up, and then he runs out of kinetic as he gets stored in gravitational energy. But actually, we only need to calculate the boost, which is mgh. So I don't think it's 550 joules, I think it's 500. We need to store 500 joules. No, above his normal jump, what energy must be stored in the spring? 15 times 10 times 1. Okay, so when the spring has got to store enough energy to launch him that high, to give him that much extra kinetic and then gravitational potential. Okay. That's right. Oh, maybe if we use 550 joules, then we can actually, okay, that implies, yes, let's use 550, actually. Because that implies that he gets compressed just 10 centimeters. Okay, so your delta y, so the idea is the spring fires, and then he's launched another 1 meter above that. Okay, we can ignore that he's physically jumping with his legs in the middle. But so divided by 500 is 1.10 meters. Okay, so the spring fires, and so in just 10 centimeters, that's what we do. Minus 1.00 meters. In 10 centimeters, 0.10 meters, we have to release all of that energy, 550. Okay, so 550 joules equals 1/2 of K times 0.1 meters squared. Okay. It's been too long since I did this problem. Oh my goodness. That's why. So remember how my little spring is like 3 newtons per meter here in class. To launch you an extra meter in the air, and I'm way more than 50 kilos, but he's a Jack Flash little guy. It would take 110,000. A very, very strong spring. Okay. Yes. It is 550. Did I write 5,500? It's 550 joules stored in. Okay. This is a J. Bad handwriting. Okay. Good, good, good. If I give another confusing question, you can just ask me. Okay, it's usually, I would specify on like a test review or the homework, it specifies distances between things. Let's do one more real quick. Oh, video. Okay, I'm gonna have to stop.